All right, so today we're going to continue, or we're actually going to finish up with arrays. And then on Friday, I will give you a tooling demo, a GDB, it's a GNU's debugger that you'll use in the week after you come back from break for your next hack. Keep in mind that, again, you don't have a class on Monday and Tuesday, so next week, no lecture on Monday, no lab on Tuesday, but when you come back immediately on that Wednesday, we'll have our midterm. I've already talked about it in the other section, so I'll just tell you right now that it's going to be that the first version of the exam worked out well enough that we're going to continue on that format. We will we'll actually let it open it up for 24 hours. So even though it's worth 100 points, it's not going to be twice as long. Don't worry about that. It will be on more recent material, but it'll be a couple of exercises again. You'll have 24 hours to do it, the 24-hour window in which to do it on that Wednesday. Keep in mind that you also have your hack due on that day, so and your reading, right? There is a really short reading though on debugging though. So my advice is make sure that you use your hack session tomorrow to its fullest and try to get as much of it done before you go off to break as possible, because you do need that material for your midterm when you get back on Wednesday. Don't waste your time on Wednesday trying to get your hack to work. Make sure that it works before that Wednesday so that you're spending the majority of as much of your time on that midterm as possible. If I had to do it over again, I would not make it worth 100 points. I'd make it worth 50, just like the other exam. But it is what it is. So, any questions? Yeah, go ahead.
That means we don't have class Wednesday.
That's a good question. So what I proposed in the other section was that class will, as always, is going to be optional. What I'll do, I will come. I'll hold class. I'll even do the live stream, but I'll do the review then, right? So a review during the midterm, 24-hour midterm. I would recommend that you do it at your convenience. If you're a morning person, I get up at 5. I do it then. Or if you're a night person, you can wait, but don't wait too long, right? And then you can watch the live stream. You can come and hang out here physically, and I'll just do last year's midterm. Right. Other questions? All right. Otherwise, they will hold help hours as usual. So, all right. So just to finish up with a couple of miscellaneous things with memory. We left off with a question of who owns memory, right? If a function creates temporary memory that it uses to process data, then it is responsible for cleaning it up. And when we say cleaning it up, we mean freeing it, right? So for example, yesterday in your lab, you fixed a memory leak. How? You gave this array that you wanted to compute the median of, right, to this function. Well, you didn't want to change the contents of this array because you just wanted to find the median. So what it did is it made a copy of that. It then sorted the copy because the median, by definition, is once it's sorted, all you have to do is look at the middle element, and it's right in the middle, right? But it wasn't able to sort the original because we didn't want you to screw up our data. We just want to know what the median is. So it made a copy, sorted it, and then found the median. But then it returned immediately without cleaning up this copy, and that was the memory leak. In that case, that function owned that memory. It created temporary memory so that it could process data. It's responsible for cleaning that up, and that's what how you eventually fix the memory leak, by making sure that you freed it up before you left that function. If, on the other hand, a function returns a chunk of memory, it's transferring ownership back to that other function. Again, yesterday in your lab, you created several functions that returned an array. And we did that also in class on Monday, right? We left off with this question of, we've got this evens array. We've got this array, and we filtered out all of the evens, and now we're storing it in this array. Who's responsible for cleaning up this array? If we did it in the getEvens function here, right, option 2, is that going to work? Free the new array. Right? How can I free something and then destroy it and then return it if it's already been destroyed? Right? That's not the correct option. The correct option here is that we've transferred ownership back to the calling function, and therefore that's where we free it. Free evens. Right? Okay? So it all depends on who owns memory. Generally, if you have memory that is owned by main, however, you kind of, sort of can get away without cleaning it up. Now, what I mean by that is, over here in main, I went ahead and cleaned it up. Right? I made sure. Right? I made sure to turn out the lights before I left. Right? That's what we're doing right here. You're about to end this program, though. Right? If you don't clean it up right here, it's not like it's going to be lost. Right? Again, memory doesn't get up and walk away. Right? The operating system will end up cleaning up the memory for you. Everything that your program grabbed, it will then reclaim. Right? So you're really, when you're freeing up memory, you're freeing it up only with respect to your program. If you have a long-running program, like a web browser or a server that's up 24/7, 24 hours a day, 7 days a week, right? You want that operating at peak efficiency. If it is grabbing memory, holding it, never giving it back, having a memory leak, that means eventually it's going to grind to a halt. It's not going to be running for 24/7 for very long, right? So in general, if you need to clean it up because it's a long-running process, then clean it up no matter what. But if you've got an ephemeral program, a program that is short-lived, right? This program, I don't know if it's compiled or not, but there, yeah, it was compiled. It runs in the blink of an eye, microseconds, right? That's real, you can probably get away with it, kind of, sort of. Right? So keep that in mind. Another thing that I wanted to talk about is how array memory actually works, right? This goes into the question originally of why do we use zero indexing? Why does our numbering in computer science always start out at 0? Well, first of all, if you're a mathematician, your count's starting at 0 too, right? Only grade school counting starts at 1. Right? You need 0 as an additive identity in the natural numbers, right? That's why then when you get far enough into mathematics, the counting numbers, they start at 0 as well, right? And the reason for this is that arrays are actually memory addresses. Right? Indexes, the plural form of index, are actually memory offsets, right, from the beginning of the array. And what I mean by that is, suppose we have an integer array called ARR, right? ARR. That's the array's name, right? The first element at ARR sub 0 is actually 0 bytes away from the memory address, ARR. Remember, ARR, it's a memory address. It's a pointer, right? If you've got an array here, here, our evens array, how do we represent that? Int star, that's a pointer, a memory address. Right? The first element stored in an array like that is 0 bytes away from the beginning of the memory. Right? Well, what about the second element? The second element is at ARR sub 1 is 4 bytes away from the memory address ARR. And you can kind of see the pattern here. ARR sub 2 is 8 bytes away from ARR. Why these increments of 4? Where am I getting that 4? How many bytes does an integer take? 4 bytes. Exactly. So here's a picture of what's going on. When you use ARR sub 0, under the hood, C is doing what's called pointer arithmetic. Right? All it's doing is saying, well, okay, there's a memory address here called ARR, and you're 0 elements away from that memory address. So 0 times however many bytes an integer takes, that gives me ARR plus 0, meaning that I start at the beginning of the array. There's my element right there. When you go ARR sub 1, then that means it's ARR plus, that's a memory address, plus 1 times however many bytes an integer takes, giving me ARR sub plus 4. Right? In other words, 4 bytes away, giving me the second element, the third element, the fourth element, etc. If this were more general, ARR sub I would simply just be ARR plus I times size of int, and it would jump to that memory location automatically. And in case you're thinking, well, if you can go by increments of 4, could you go by increments of 1? Yes. Could you go by increments of 5? Yes. Could you go by other weird increments? Yes. You would be doing your own pointer arithmetic. You'd be royally screwing up the memory, but you can do it, right? You'd be writing half of an integer and another half of an integer if you wanted to do something like that. Right? For that reason, remember that we said, let's look at the example up here. When we were looking at the filter or the get evens here, right? And I said only set it once at the end, and I told you that if you did something like this, that it would be wrong. Because this increment goes to the next byte, right? If you're at a certain memory address, this memory address right here, plus, that's moving 1 byte over in the memory space. Right? 1 byte over, 1 byte over, 1 byte over. Don't do that, right? Oops, didn't want to get rid of all that. Evens, there we go. All right. The truth is, this is syntactic sugar, right? Some hardcore C programmers will do all of their manual pointer arithmetic themselves. Sometimes you have to if you're doing something called generic programming. If you want to write one function that operates on any type, you basically have to tell that function that the types that this takes are 4 bytes or 8 bytes or something like that. You saw a preview of that in your lab. How did we sort? We use this built-in function called qsort. There's only one qsort function. There's not a qsort function or sorting function for integers, a sorting function for doubles, a sorting function for whatever, right? There is one function. The way that it sorts is by you telling it, well, each item takes 4 bytes. So I've got 4 bytes over here and 4 bytes over here. If these are out of order and I need to swap them in order to sort it, all I need to do is take these 4 bytes, move it over here, take these 4 bytes and move it over here. The same function can be used to sort doubles, in which case you've got 8 bytes and 8 bytes and you're swapping 8 bytes and 8 bytes. All of that stuff is generic programming and we're not going to get too far into it. What you should know, however, is this pointer arithmetic and what's going on behind the scenes. Otherwise, use this, right? Just use regular old indexing. Right? And this is why virtually every language follows this, because that index is nothing more than an offset. It's a memory offset. Right? Some questions online. When is the review for our midterm? Yeah, it'll be Wednesday during the midterm. Right? Okay. Okay. So that's how memory actually works, right? It's just an offset. The compiler and C are doing all of the arithmetic for you by using this this indexing scheme over here. Right? Neat. It does something for me at least. Right? The last thing I want to talk about, and then we'll talk about the lab here, are shallow versus deep copies. Right? So what's a shallow copy? Example, shallow copy demo. I've got that loaded up over here in Python Tutor. So I've got a snippet of code here. Let's read through it. First of all, I create an integer n5. I'm going to create an array of size 5. There are going to be 5 things in this. I call malloc, and I set that up, and so I've got now an array of 5 elements. I walk through that, and I set them to 10, or 0, 10, 20, 30, and 40. Okay? Now observe line 9 here. I'm trying to create another array, BRR instead of ARR, right? The second array. And I'm going to make it equal to ARR. Right? Now, if this were a regular variable, x and y, right, and say that x holds the value 42, and I assign y the value of the value of x, that's taking a copy of the variable 42 and it's copying it into this variable over here. We've got 2 different variables. But what happens when you've got arrays? Right? All I'm doing is what's called a shallow copy here. I'm making that second array point to the first one. Look at the visualization of this. I'm going to have 2 pointers, but they point to the exact same array. Right? When I change BRR sub 0 to be 42, what's going to happen with respect to A? It's also changed. Why? there's only one array here. There's only one copy of the array. I have two pointers to it, and it's referring to the same thing, right? So it ends up changing the array for both of them. Here, I'll prove it. Printf, ARR sub 0 is now equal to %d, ARR sub 0. There we go. Visualize this execution, and I'm just going to fast forward all the way to the end here. You see that it actually prints out 42, right? This is known as a shallow copy, right? And it kind of makes sense because of the demonstration that we originally started all this out with, swapping, right? When we passed by value, we had two distinct copies, 10 and 20, and those copies got swapped. When we pass by reference, we're passing pointers. So we've got multiple references to the same thing so that this thing can change its value so that this thing can see the change. And that's what's happening here. We've got one reference to the same thing, right? A shallow copy is when you have more than one reference, or you could have 2, 3, 4, 5 references, whatever, to the same thing. Changes to the array are reflected in both references, right? In other words, both pointers, right? In contrast, what's the opposite of shallow? Deep. A deep copy would mean a completely different copy of the array. So that changes to one do not affect the other. All right? So let's go back to our Python tutor over here, edit this code, and rethink what we're doing on line 9. That's a shallow copy. I'm going to go ahead and make sure that you've got it in the notes, shallow. Right? Otherwise, let's go for a deep copy. Right? I want BRR still. Right? What am I going to have to do if I want a completely different and separate array? I'm going to have to create it. Right? So how do I create arrays? Int 5. Is that correct? Nope. Is it BRR, so 5, because there are 5 things in it? You could do that, but what kind of array is that? It's a static array, and you've already seen the limitations of it. The second exercise in your lab yesterday was fixing this issue. You can't return this from a function, right? You should exclusively use dynamic arrays, almost always. Right? So how do I create a dynamic array? What's that thing called again? Malloc, right? I need to typecast the return type here. And how big do you want it? 5 integers? Nope. How did I do it up here? However many you want times however many bytes each one takes. Okay? All right? And now, if I were just to run this, what would be in the contents of BRR right now? Well, let's find out. Come on. All right. Fast forward, in fact, fast forward. There we go. There's the contents of A. BRR is going to be a brand new, separate, completely different array. But what's in it? The same stuff? That ain't a copy. So what else do we need to do? Copy over each value. For int I equals 0, I is less than n, I plus plus. BRR sub I is equal to ARR sub I. Oops. Now let's visualize all of this together. Okay? So I'm going to go ahead and fast forward just a bit here, because we've already seen this, right? So I filled the contents of A. I create BRR, which is a completely different array. It's a deep copy. And I go about copying over each element from the original. Right? Now I've got 2 distinct copies, 2 arrows pointing to completely different things. This is a deep copy. Right? Changes to BRR now. Are they going to affect ARR? Nope. Only BRR is changed. When I print out the contents of ARR, it's still 0. Right? So if you ever have a use case where you need to process data, but you need to keep the original data without affecting it, without changing it, right? Then you want a deep copy, right? Because if you don't have a deep copy and you just have a shallow copy, you have multiple references to the same thing. one of them changes it, the other one sees that change. Right? One of them can screw up the data for the second one, so you may not want that all the time. Okay. In fact, this seems so, I don't know, useful maybe, that maybe you should put it in where? A function, right? In fact, that's what I'm not going to do that. Why? Because we gave it to you in yesterday's lab, right? If you want a deep copy function, you can go ahead and cut and paste that. This is why we give you code, right? Right. All right. With the remainder of our time today, first of all, any questions? Yeah, go ahead.
I don't know specifically yesterday. I think they might get it, but how come with a normal array, I can't figure out if you use a pointer to use a pointer and malloc for the array, then the other one just using normal integers?
Which one?
For
Like a static array?
yeah, if you're making a static array, it's just a normal one. But what if you're making like a 2D array? You have to do the two asterisks, right?
Yep. Yep, that's because that's 2 dimensions.
Can you only make a two-dimensional array with malloc?
You can only make dynamic arrays. Doesn't matter what dimension they are. You can only do it with malloc or calloc or realloc. But yes, so let's actually look at that example. So you could do something like this: int sir, or let's say with table 2, 3. You could do something like that. That is a 2-row by 3-column table, but this is a static array, right? If you did this inside of a function, you wouldn't be able to return it. You wouldn't have been able to do something like this in your lab with like the get multiplication table. The wall flag would have yelled out to you, you are returning a non-allocated local variable of some sort, right? And when you get back to the function, that stack frame has been popped off and it's gone, right? I'll show you, right? Let's go int star mult table, right? Int n. If I did something like this, and I filled it up with whatever values it should have, and I tried to return table, right? Let's visualize. Let's actually call it int star table is equal to mult table of, I don't know, 2 by 3. Right? I'm not even sure if this will compile or if that's going to be a fatal. Okay, it did. All right, there we go. So we're in main. We do all that stuff. Yeah. I don't want to lose that code because I want to use it. Now we're about to call another function. Where does that table live? Does it live in the heap? Nope. It lives in the stack. In fact, it lives in the stack frame here of mult table. Right? I don't actually do anything with it. So as I'm about to return, what's going to happen to that stack frame? Gone. Deleted. Goodbye. So what value does table have here? I couldn't return that thing because it's already been deleted. Right? So what would you have to do? Let's go ahead and get rid of this. We'll come back to it if we want. Let's go ahead and create a, I don't know, let's make it a little bit bigger, 3 by 5 table. Right? So remind me how I do this. I need a double pointer because it's 2 dimensions, right? Table. I'm going to create the array of pointers where each pointer is going to point to a row. Okay? So that's going to be a call to malloc. The cast has to match the left-hand side. Malloc. How many rows do you want? N rows. How many bytes does each pointer in each row take? Each one is going to be an int, or size of int star. Right? There we go. Now that only sets up the array of pointers that point to each one of the rows. I now need to set up each row. For int I equals 0, I is less than n number of rows here, I plus plus. Table sub I is equal to call to malloc. Now this is just a regular call to malloc that we're familiar with already. M times size of int. Because there are m items, m columns in each row. Here's one row, and there are going to be m columns in it. let's take a look at what that looks like, and we're not doing anything with it, but at least we'll be able to visualize this. We're going to have what topics will be on the midterm? So everything in module 5, 6, and 7. So 5 was functions, 6 was pointers, error handling, et cetera, pass by reference, and then of course 7 now is arrays. Right? So let's walk through this. 3, 5. I've got my array of pointers. Right? Now, it's depicted it horizontally. Well, the way that I depicted it yesterday or on Monday was vertically, so that each one would point over to a row. But it's going to turn out to be the same thing here. The first pointer will point to the first row. The second pointer will point to the second row. The third pointer will point to the third row. In effect, you have a 1, 2, 3 by 5 table here. Right? Once you've got that, you can go ahead and treat it like a two-dimensional table. Table of 0, 0 is equal to 42. Right? Does that help? Or not? Or
Well, I think I understand that. I was just confused on whether you could even make it 3D array or you needed to make it a pointer or.
yeah, the way that I'm showing you, you need a double pointer here. Now, there are alternatives. If you watch the pre-prepared videos, I go through at least 2 other alternatives that I won't go through here because of time. And also, if you go down that path, make sure that you know what you're doing. There, it's going to be some pointer arithmetic involved, where if you allocate one contiguous chunk of memory, and then you set up your pointers to point to. It's like one big giant row, right? So instead of 3 rows, each with 5 things in it, I create an entire array with 15 total. And then I make sure that the first pointer points to the beginning, the second pointer points to 5 over, the third pointer points to 10 over, right? And that's that's the alternative. If you're interested in that, watch the pre-prepared video or read, not Zybooks, but my book, right? Again, keep it simple. Do it how I've shown you here. Okay? All right, so with the remainder of our time, I thought we would just jump over here to the lab. For the most part, the lab scores were pretty good. We did see some some oddities, right? When something fails, right, it's not going to necessarily be apparent on your machine, right? Everything could print out just fine. That doesn't mean that there's not undefined behavior. Right? The grader is going to be far more rigorous. It's going to be running like 100 or 1,000 different test cases. It's going to be trying to break your code. Unless you try to break your code with the same rigor, you're not going to be able to see these errors manifest themselves. So what tool do you need to use to see those hidden errors? Valgrind, exactly. 1, always compile with the wall flag. About 70% of your problems can be pointed out by the compiler. Right? Address all of those warnings. That was the first and second exercise. 2, make sure that you're rigorously testing. The people would ask us, what's wrong with my filter function? When we looked at their main, they hadn't even bothered testing it. Right? They just threw it in the grader and were testing blindly. At least have one test case. Right? See that it's at least working and giving you something. If it works and it's not erroring out, then third, bring up Valgrind and try to find out what other errors are going on without a full seg fault. So with that idea, we gave you most of this stuff. This is where it starts, I think, right? Get mean. Let's see, 20 minutes. All right, so nominate a function here, and let's do it. Go ahead. Okay. Filter threshold. I'm going to end up cutting and pasting every single line of code from getEvens that we did on Monday. The only difference is going to be what? Instead of checking to see if it's even, check to see if it surpasses that threshold. Right?
What is the function return? That was what giving. I couldn't return the function. That was
Return the new array?
yeah. That part never worked. I was had doing what and like an hour ago talked to people in
I'd have to see what it is.
Figure that out.
Okay.
Things like slate colors and something like that.
Okay. Yeah.
I think I was having the same problem as him. I just got lost in the pointers. Is really what happened.
Okay. So let's ignore this code, and let's start fresh. All right. Filter threshold. All right. Ignore everything that we did. All right. And we'll do it all again. All right. All right. Let's go ahead and document this. I don't think that anybody had any problems understanding what the function should have been doing, right? But let's go ahead and run through a whiteboarding example here. So this function takes an array of integers of size n and returns a new array containing only values that are greater than the given threshold. Greater, right? Okay. Greater than or equal to. Or equal to. So there's our input. Choose a threshold for me. 5? Okay. All right, I like that. So let's walk through it and understand what would end up in this final result. 5, because that's greater than or equal to 5. 8, yes. 3, nope. 4, 2, 0, 6, 9. There we go. That's our expected result right there. Okay? Now, basic error handling here. What could go wrong with the array, the size, the threshold, the result size? What could go wrong with ARR? Null. If that's null. Or what could go wrong with the size? Negative. You can have arrays of size 0. It's kind of useless, but you can do it, right? You can ask malloc for 0 bytes. It'll oblige. There's a memory location over there for 0 bytes. Don't use it because you can't. Or what's wrong with the result? There's nothing wrong with threshold here. It's just a number, right? What about result size? If that's null. Why? Because it's a pointer, right? Another common error that we saw was, can size ever, should I check for null for size? Is size a pointer? No. There's no such thing as a number being null. A pointer is null, right? This is not correct, right? By the way, what is the, yeah, go ahead.
Does it matter if result size gets passed in null anyway? Because we're going to end up changing it inside the function.
If you end up changing it inside the function and it were null, result size is equal to 42. What are you doing? Bret Hart is going to knock you upside the head. You are dereferencing a null pointer. Don't do it. Right. What is the point of result size again? The size of the resulting array is, is placed in the pass by reference value result size. Right? I need to know how big this array is. It's of size 4, right? If you put it on me, I'm calling you, you're the function now. If you put it on me to know how big that is, I'm doing half your work for you, right? I want this function to do all the work, right? Including telling me how big the result is, okay? All right, if we've got an error here, what can we return? Can we return 0? We could, but what is that? 0 is a number. What do we return? A pointer. What's the only pointer that will get us in trouble? Null. Right, there we go. Otherwise, step 1. Let's determine how big the new array should be. ... By counting the number of elements greater than or equal to threshold. Okay? So, int count. I'll start it out at 0. Failure to start something at 0 is an uninitialized variable. Garbage plus 1 is garbage. Make sure you initialize it. 4, int I equals 0. I is less than, what, size? I plus plus. Right? Count plus plus, or not if, I guess. If the ith element is greater than or equal to threshold, right? Then count plus plus. Right? When I'm done with this loop, I know that count is the size of the array. I've gone through and counted 1, 2. Nope, no count, no count, no count. 3, 4. Right? I know how big the result should be. Now, create the array. Create the array. Dot, dot, dot. Can I do this? Int result of count. Can I do that? I can, but what kind of array is that? It's a static array. Can I return that? Nope. It disappears with the stack frame once it's destroyed. Int star result. I have to use dynamic arrays. This is so much of a problem. I always debate each year of not even telling people that static arrays exist. Unfortunately, every goddamn C tutorial out there starts with static arrays. So if I don't address that issue up front, everybody will see these tutorials with crappy static arrays and think that they can use them, right? I start out showing you, here they are, here's why we don't use them, only go with dynamic arrays. Right? Yeah?
Is it okay to like ask for more memory than you use it? You're like, well, I know it's not going to be what it is.
Yeah, so we saw that too. We saw some people skip this step entirely and just say, well, size is big enough, right? Times size of int, right? I'll just make it as big as the original array, right? And then ultimately I'm going to end up, you know, having dummy wasted memory at the end, right? That's not ideal, right? Now, granted, you're probably only wasting a few kilobytes here and there or whatever. Maybe you're not even wasting anything because of page, you know, how memory actually works. But it's definitely a code smell, right? You're wasting memory for no reason, right? Now, what you could do is you could make a deep copy, right? Then go through and get rid of all the elements that you wanted, right? And then copy only over part of it, but that's more work than probably than what we're doing here. Right? All right, so size, nope, count. In fact, I like to call this new size, right? New size, and new size. Right? Don't just call it count. Count. What are you counting? Right? Are you counting evens? Are you counting odds? Are you counting thresholds? Above, below, whatever? No, just new size. Right? Not only that, but now that we know the new size, where should we be putting that? In the result size equals new size. Is that correct? The left-hand side is a pointer. The right-hand side is a regular old variable. What do I do to a pointer to turn it into a regular old variable so that I can set it? Dereference. Done. That's why, again, I need to make sure that I'm checking null up here. I've created the array. Now, 3, copy over the elements, but only if they are greater than or equal to the threshold. So I'm going to steal this code again, iterate over the elements, and if they're greater than the threshold, then I copy them over to the, what was it called, result sub something is equal to array sub I. Right, there. Now, why did I put question mark here? Should I put I? Nope. What would I end up doing? I would definitely, eventually I would be like over here, I would be in the memory space that I don't have, but but I'd also be copying things over in the wrong location, right? For example, 6 should not be at index 7. It should be at index 2, right? So let's come back over here and establish a new index. Int j. I'll start it out at 0, and I'll use it like that. Now, if you've copied over one element, you need to increment j so that it moves along. Finally, returning the result. There's filter threshold. Let's see if it works. For this one, I will use a static array. Primes. No, forget it. Let's grab what we were using, right? This one. Let's just use this. Oops. Foo is equal to this. And then int filtered is equal to, what was it called? Come on. Filter threshold. I pass in foo. The size of foo is, which is 8, right? Int size of filtered. Right? And what else do I need to pass? Oh, the actual threshold and then the result size. So the threshold here, you said 5, right? All right, and then the size of filtered. Why did I put an ampersand in front there? Because I need to reference it. It's a regular old variable. It expects a pointer to a variable. Therefore, I reference it. Now let's visualize this. I don't actually need to print it out in the main. Oops. Fine. Null is undeclared. Where is it declared? In the standard library std lib.h. There we go. Being very pedantic there. Semicolon. Fine. There we go. Forget you. All right, let's watch as it moves along here. There's foo. Come up here to filter threshold. We end up referring back to foo and size of filtered here. Do all of our checks. Great. Everything checks out. Fine. The new size is 0. Right? We run through each element. Now, there's no visualization there. It's just going through this. But you'll notice here that the new size, it's counting up 2, and it won't change until we get down to the last one's 4. Right, there we go. Watch size of filtered. It's going to receive the value 4. It's kind of hard to see because the arrow is on top of it, but it's there. Right? And I can't move this stuff around. Can I? And increasing the size or whatever, it doesn't work. Okay. All right. Now we create an entirely new array that is on the heap because we need to return it. Right? If it were in this stack frame right here, it would be destroyed on its way back. Right? And we run through that. When we get to 5, we include it. When we get to 8, we include it. Right? You'll note here that I is increasing, but j is not. We're skipping over those other values. And then we finally copy 6, and we copy 9. That was the result that we expected, right? And then we return to the function. Right? There we go. And that's it. If you want to use Python Tutor to visualize this kind of stuff, you should. But unfortunately, this tool is kind of persnickety. You have to basically have compilable and segfault-free code to begin with to visualize it. Right? So to solve that problem, on Friday, we're going to look at a proper debugger called GDB. We do have 7 minutes left. Any others? No? Yeah, go ahead. To print out? That's why we gave you a print table. So, real quick here. Not here? Okay, let's do it here. How would you go about writing this function here, first of all? Let's go back to our notes. Right? I'm going to steal this code right here that we did in class on Monday. Right? All it's doing is creating a table with n rows. For each row, we create m columns. And instead of setting each one of them to 0, what should I set it to? I think +1, right? +1 times j +1. There we go. And then I need to return the table. If you're not returning the table, you're not returning anything. You're not receiving anything. So down here, let's go ahead and grab it. Int mult table is equal to, what was it called? Create multiplication table. We'll do, I don't know, keep it small, 3x4 table here. Right? Now, if you were just to print this, what would it look like? Print table. I give it the table and the dimensions 3 and 4. Right. If we want to really quick, yeah, we've got time. We gave that to you, right? So where's that print table? I'm going to steal that code and come over here to Python Tutor and add that at the top. Now it's kind of unwieldy. This is why It's a good tool for very simple visualizations, and that's what I use it for. But it's not a great tool for, oh, print array. All right, fine. Got to steal more code. There. Come on. All right, great. There we go. Run through this code really quick. So I'm going to have n and m, 3 and 4. Initially, the table, just like we visualized before, is going to be an array of pointers. Each one of those pointers is going to point to a row of size 4, and we're initializing it as we go along here, 1, 2, 3, 4. The next one should be 2, 2, 4, 6, 8, right? The next one should be multiplication table here, 3, 3, 9, 6, 9, 12. There, yeah, there we go, right there. And then ultimately we return from it, and we come back into our main function here, and I'm going to jump all the way to the end there, and it prints it for you. Okay. One last thing. This happened in my sections in Omaha, but I don't know if it was all prevalent down here, but there was some confusion as to the difference between, say, get the minimum and get min index of min, right? So hopefully we understand indices a little bit better now that we've had some practice with our arrays. But if I gave you this array right here, what's the minimum element? 0. What's its index? The indices are 0, 1, 2, 3, 4, 5, 6, and 7. Get min would mean that you're returning 0, the actual minimum value. Get the index of min means tell me where it is. Right? Which one of those, by the way, is more general? Which one gives more information? Min index, right? It's telling you, there it is, it's over there in index 5. If you want to, you have access to the array, you can jump there and find out what the minimum value is, or the maximum value is. The expectation on these two functions was that you would actually call get min index of min from this function right here. Right? It should have been, this one should have been just a one-liner. Give me the index, and I'll use the index to actually get the maximum or the minimum and return that value. Right? Get min should have looked something like this. Let me do it up here. Get min, right? Int index is equal to get index of min, array and size, right? Return array sub index. Right? Or better yet, code golf, right? One line.
I had the idea, but I was looking back at those and I was trying to
Yeah, if you have functions, make sure that the most general function is the one that gives the most information. In fact, this is something fundamental in computing called a reduction, right? So if you can solve one problem with the solution to another problem, that means that that problem reduces to that problem, right? So finding the minimum, or finding the minimum, finding the max, getting the minimum, you can use one solution to solve both of those problems. Right? That's a reduction. Look for things like that. Your hack is especially set up so that you don't have to write too many locks. Locks are lines of code, right? So, in fact, yeah, we've got 1 minute left here. Was there Reddit programming lines of code big brain? No, that's not going to come up. Dang it. I wish I had kept it. There was an image of the beginner programmer writing 5 lines of code an hour. The intermediate programmer writing 100 lines of code an hour. The advanced programmer writing 1,000 lines of code an hour. And the expert guru programmer writing -2 lines of code an hour. Why? You're getting rid of the cruft. You're getting rid of the stuff that you don't need. Why do we need that function? We've got a built-in function over here in the language. Let's use that, right? getting rid of unnecessary code, taking verbose code and simplifying it down to simpler code, right? Excellent. Keep it simple, engineering.